people try to give examples of higher rank arithmetic groups which are boundedly generated. And the main reason for these attempts was that it was known that if for finite completion of a higher rank arithmetic group is boundedly generated, then this group has the congruence subgroup property. And one way to prove that the for finite completion is boundedly generated is to prove that the group itself is boundedly generated. But nobody was able to give such example. And I think last year it became clear why nobody succeeded. It's simply because it cannot happen. So Korvaja, Rapinchuk, Ren, and Zanier proved that anisotropic arithmetic groups are never boundedly generated. So you cannot use bounded generation in order to prove the congruence subgroup property in the remaining open cases, because all these cases are anisotropic. But the theorem is quite surprising because we do not expect that there would be such a difference between anisotropic groups and isotropic groups. Usually, these two subfamilies of groups have similar properties. So we want to understand what happens.
Now it's too loud. I think it's clearer now, but it's...
Alex, is it okay?
And I'm sorry, there is a little bit some problems with the voice, so we are trying to fix it to make it optimal.
I see. So
talk now.
Okay. So what is the difference between the anisotropic case and the isotropic case? And so if A is unipotent, then the entries of the nth power of A are polynomials in N. Well, if A is semisimple, and you can think that A is actually a diagonal matrix, then the entries of the nth power of A are exponentials in N. And if you think about it, it's higher rank arithmetic group, so bounded generation leads to equations. Let's say that you are a product of k cyclic groups, you get equations, and so if you take unipotent element, you get polynomial equations. But if you take semi-simple equations, semi-simple elements, you get exponential equations. And it's much harder to solve exponential equation than it is to solve polynomial equation. So essentially, this is the reason why you can't have a why anisotropic groups cannot be boundedly generated. I guess that at some point there will be a talk about it, but this is the essential point. Okay, so I will get back to this point in a few minutes, but I want to give a definition. By the way, Alex, I have until when?
Yeah, you can you know.
No, he asked what when? What? He asked how much time.
How much time? 75 minutes altogether.
Okay. So I think it would be less, but that's for sure enough. So definition, let gamma be a group and X an unempty subset of gamma. The width of X is the minimal n, and n can be either a natural number or infinity, such that every element in the subgroup generated by X is a product of at most n elements of X, of elements from X or their inverses. So for example, if you think about bounded generation just means that you have finitely many cyclic subgroups. such that the union has a finite width. This is what a bounded generation is. And Carter and Keller were the first to prove bounded generation. They proved that SL and O and n greater or equal to 3 and O is the ring of integer is boundedly generated. So they had a proof of this fact, but later they gave another proof together with Page, and the later proof uses model theory, but not in any essential way. Just it uses ultra powers to avoid computations. But what she actually proves is the following: that the SL and O conjugacy class of the elementary matrix E1n, which is the matrix with 1 on the diagonal, 1 on the 1n entry, and 0 elsewhere, have a finite width. And I should say that this theorem really uses the fact that O is a ring of integer. This theorem is not true for general ring. It's even for Euclidean rings, it is not true. For example, it is not true for the polynomial ring over the complex number. And there is the following theorem of Sustained. So n is greater or equal to 3. So there exists a constant C such that for every commutative ring R, every element in the SL and R conjugacy class of E1n is a product of at most C elementary matrices. So if you combine Sustained theorem with the theorem of Carter, Keller, and Page, you get immediately bounded generation, right? Everything is a product of finitely many elements of the conjugacy class of E1n, and every one of these elements is a product of finitely many elementary matrices. Now, the point that I want to make is that the part that uses the arithmeticity of the ring is the part where you prove that the conjugacy class of E1n has a finite width.
Chen, just
yes.
In the Sustained theorem, the constant C depends on n, I bet, right?
Depends on what? It depends on n.
On n?
Yeah, but not on the ring R.
What?
It depends only on n, not on R.
Depends only on n and not on R.
Yeah, you can see it, right? Because you take an ultra product. If it was dependent, if it depends on R, then you take an ultra product and you will get a contradiction. Yeah. Okay. And now I want to go back to the first point. If you take two matrices in SLN, A and B, and think of A as a matrix with constant, and B as a matrix such that its entries are variables, then the entries of the conjugation of A by B are polynomials in the entries of B. And this is, and you don't care if A is semi-simple, unipotent, it just doesn't matter. So if you look at conjugacy width, which implies bounded generation for SLN, and I believe that also for many other isotropic groups, then you always get polynomial equations, even if you work with anisotropic groups. So what I or me and Nir want to suggest that maybe this is a better property to look at than bounded generation, because there is a chance that this property will hold in anisotropic groups. Okay. But as I said at the beginning, one of the reasons that bounded generation was an interesting problem was that it implies the congruent subgroup problem. So here is a theorem, and I wrote some part of the theorem in purple simply because this is the setting that I'm going to use again and again in this lecture, that I don't want to say it again and again. So I say it once and for all, and it is written in purple. So let K be a number ring, S a finite set of places of K containing all the Archimedean ones, O the ring of S integers of K, and G connected, simply connected, an absolutely simple group scheme over O, such that for every finite place V, G of KV is isotropic. So G, and these are the conditions that you need in order to have a chance to have the congruent subgroup property. GO as the congruent subgroup property if and only if every conjugacy class of the profinite completion of GO has a finite width. So exactly as we had with bounded generation, we have with conjugacy width. But I want to say that if every conjugacy class has a finite width, then you have the congruent subgroup property. And therefore, it's not hard to see that not only that every conjugacy class has a finite width, but that you have a global bound on the conjugacy width of about the width of conjugacy classes. No matter which conjugacy class you have a bound, you have a constant C, which bounds the width of all conjugacy classes in your group. So the problem now becomes to find condition on GO, which implies that every conjugacy class in the profinite completion has a finite width. Now, it's not clear that it is enough that every conjugacy class of GO has a finite width, because maybe this width can get larger and larger. And then when you take the limit, you get a conjugacy class with infinite width. So I don't have such an example. To be honest, I didn't try to construct such an example. I don't know if it's easy or hard to construct it, or if it's true that there is a counterexample. But anyway, it's not clear that it is enough. But what will be enough is that if you have a constant C that bounds the width of all the conjugacy classes, then this will be enough, because you will take an element of a sequence of elements, you have a uniform bounds on the width of their conjugacy class, and this bound will pass to the limit. So, so this is what the first thought is, that let's try to prove something like this, and if you look at SL and O, then everything works. You have a uniform bound on the width of conjugacy classes, and I believe we didn't prove it. I believe that it will be true in all isotropic cases. So it looks good, but if you think about it slightly more, you understand that this cannot happen if you are an isotropic lattice. You cannot have a uniform bound, and let me explain why. So let n be greater or equal to 5, and F will be the standard anisotropic quadratic form. Maybe I should say I will talk about high-rank arithmetic groups in general, but all of the interesting examples that I will give of anisotropic one will be orthogonal groups. So the groups gamma, which is spin or F of the localization of Z by 2, and if you don't know what is spin, then forget about it. You can think about SO. Is dense in the compact group spin F of R. so what you get spin, so there are elements in gamma whose conjugacy class is arbitrarily close to the center of the spin over the real number. But now here is the problem. This group spin over the real numbers is a simple group. So if you take a non-central conjugacy classes, it will generate everything. But if you start with a conjugacy class that is very close to the center, and you start to multiply it, if you multiply a small number of times, the element will still be very close to the center. So it will take you a lot of time to cover everything. And you can start with conjugacy classes which are closer and closer to the center. So at the end, so you cannot have a uniform bound. So at first, it seems really bad. But then when you continue to think about it, you say, wait a minute, even if forget about such complicated situation, even if you try to solve polynomials, just one equation, in order to have a chance that you have solution with integral coefficients, you have to have local solutions over the p-adix numbers for every p, and solutions over the reals. Otherwise, there is no chance that you'll have solution in the integers. So this leads to the following conjecture. So let K S, O, and G be as in Theorem 1, and denote by T the finite set of places V in S such that GKV is compact. And remember, by our assumption, such V are necessarily real. So the conjecture is that there exists a constant C such that for every G in GO, the width of the conjugacy class of G is at most C times the maximum of the width of the conjugacy classes of G, but in the groups GKV, where V run all over the finitely many places in T. So you might wonder why we run only on the places V and T, but it's not hard to see that you do have a uniform bound on the conjugacy width of G all over over the other places. So the really places where the problem can come from is the places where GKV is compact. And in fact, this formulation is strong enough to prove that in the profinite completion, every conjugacy class has a finite width. This is an easy exercise. So this is the conjecture. Now, I just want to say one more thing about the conjecture.
So this will give you that in the profinite completion,
yes,
you have a bound or you have a universal bound independent of the conjugacy classes.
It will give you a universal bound, but
even a universal. You're basically saying that all the obstructions are in the compact completions of the group gamma. Right. Once you get rid of them, the rest is just like isotropy.
Yes, exactly. So this is the conjecture. And this conjecture is likely to play it safe. It's not safe in the sense that we don't know it in many cases, but it's safe because we take C to be a multiplicative constant. But if you, at least in isotropic cases, it looks like it might be an additive constant. It's not multiplicative constant C plus this. So you don't have this max, so T plus this maximum in some sense, okay? So it will, okay, I don't want to, okay, so maybe even a stronger conjecture is true, but this is something that we do not know even how to give example in anisotropic cases. And we will see in the second part of this lecture that we can give anisotropic groups for which the main conjecture is true, if you take C to be a multiplicative constant. But I want to say that this conjecture is really a conjecture about higher rank arithmetic groups. It's never true in rank 1 arithmetic groups. So I don't think that it's written anywhere in the literature that it cannot happen, but what is written in the literature is that if you take any word in a cylindrically hyperbolic group, which include all rank 1 arithmetic groups, then every word you have a dichotomy. Either the set of values of this word is already everything, and this happens if and only if your word is a primitive in the abilization of the free group, or this word has infinite widths. So it's a much stronger theorem in the sense that you take the union of many conjugacy classes, right? The set of word values is the union of many conjugacy classes, and it should be, I didn't write the details, but you should be able to use the same technique to prove the simpler statement that I'm saying, that it cannot, that this conjecture is never true in rank 1 arithmetic groups.
This is the theorem or conjecture about the hyperbolic group that
No, it's a theorem. It's a theorem of, okay, Bestvina and others. I don't remember who are the others, to be honest. It's a theorem of 3 people. So the story is that it was first proved to the free group by, sorry, I forgot. And then,
but I'm interested in the first part. I can understand. The second part is probably using bounded cohomology. The fact that
no. It's not using bounded cohomology. It's using some the action. It does not use bounded cohomology.
Well, quasi-homomorphism.
Yeah, it uses.
But
in
the first part that you said that if it's onto, if and only if the word is primitive, this is
right.
not a hyperbolic group.
Yes. So yes. This is even before Bestvina. This is Meisnikov and one other person, which I again forgot the name. Hyperbolic. It's the relatively hyperbolic and hyperbolic. It's really very similar proof once you know enough properties of relatively hyperbolic groups. So it's yeah.
Interesting. Okay.
So I just want to state the main conjecture in a different language, which is in some sense a more conceptual language. I will get back not to it a bit later when I talk about an example. So the different formulation is the following. So under the assumption of the main conjecture, fix an unprincipled ultrafilter U on the natural numbers. Let O star and K star denote the U ultrapowers of O and K respectively. For every G in G of stars, which normally generates GK star, and here is the important part. We usually think that spin groups are simple or simple modulo their center. If GK is anisotropic, then GK star is not simple. It has a larger a largest proper normal subgroup, and everything that's above this subgroup is everything, but it's not, and the subgroup is far from being central.
Well, I mean, and GK is not simple because you can embed it into compact groups and the periodic, completions into finite groups. Basically,
excuse me?
What?
Why GK is not simple?
No, I mean, I've said that even G of K is not simple, not just G of K star, but the Platono-Margulis conjecture predicts that the only normal subgroups are those which come is a kind of, in spirit, it's similar to your conjecture, the Platono-Margulis.
No. But I'm saying that if G is spin, for example, and in all finite places, you are not compact, then the Margulis-Platonov conjecture tells you that you are simple. Right? So even in these cases, GK star is not simple. Mm-hmm. If it's anisotropic. Yeah, you are right. It's not always simple, but under the condition that I wrote, at least when G is spinned, then it is simple, and still G of K star is not simple. So if you take an element with it in G of star and it sits inside this infinite index normal subgroup, then it does not have finite widths, but this is the only obstacle. The normal subgroup of GO generated by G, assuming that G generates GK star, contains a finite index subgroup of a principal congruent subgroup of GO star. So in a sense, this is a formulation of Margulis normal subgroup theorem. If you say what this theorem tells you in the standard case, then this is exactly Margulis normal subgroup theorem. But when you pass to a non-standard model, or let me be more careful, to a saturated model or a ultra power, or a ultra power, then all this theorem become the same. Margulis normal subgroup theorem, the congruent subgroup theorem, the conjecture about widths of conjugacy class are the same theorem if you work with a saturated model of your group.
So, like if you go to this ultra power, then you say that all this theorem becomes give you the same conclusion, but you cannot go backwards because
you cannot.
The Platono-Margulis is known in many cases, for which the congruent subgroup property is not known. You cannot go to the infinity and come back, right?
No, you cannot use, no, because you don't. So one of this project is that once you understand that it's the same, to use other proof, like a proof of Margulis normal subgroup theorem or something like this, to prove this in an ultra, in a non-standard model, and then to get the congruent subgroup property in the standard model. But we don't have an example when we actually can do this. We don't understand what is the, okay, we don't have such a thing. Okay. So okay. So this is just I think very conceptual to understand why you do want to think about this group, also about non-standard models of them, because they contain information also about the standard model. Okay. So the second theorem, which is an example where the conjecture holds, is the following. Let n be greater or equal to 10. F is the standard anisotropic quadratic form on 2n variables, and O is the localization of Z at 2. G is spin of F, and gamma is G of O. Then for every m greater or equal to 2, the set of m powers has finite widths in gamma. And okay, so this is not one conjugacy class, and this is many conjugacy class together. all m powers. But still, this thing is never true for rank 1 arithmetic groups. So there is really something non-trivial going on here, and this is an isotropic group. But if you assume the general Riemann hypothesis, we can prove the actual conjecture that you have bound on the width of conjugacy classes. And the use of the general Riemann hypothesis, at some point in the proof, we need to use some version of Artin primitive root conjecture. And Artin primitive root conjecture is fully proved only under the general Riemann hypothesis, at least for some extension. You don't need you don't need it for every extension, for every number feed, but I think that just for a billion or something like this. I don't remember exactly, but there are slightly weaker versions of Artin primitive root conjectures, which can be proved without any assumption, without the general Riemann hypothesis, and it might be possible to use these things in the proof together with the proof that I'm going to present to actually give unconditional proof, assuming that O has enough units. So we didn't try to do it because we are not from number theory, but I think that at least for examples, you can avoid the use of the general Riemann hypothesis, but we didn't do it. Okay. So in the rest of this talk, what I want to do is I want to briefly explain the proof. Not briefly, it will take some time, but to explain the main step of the proof, because in some sense it's similar to the proof of the congruent subgroup problem or property in the standard model. And what I ask everybody, please feel free to stop me and to ask questions, because if you know because I would try to distinguish between the essential details and the technical details, but I think that maybe that it's possible to understand at least the big picture, maybe not every small detail in the proof, if you will ask questions. So the main steps of the proof is to show that the width of X in X will be a conjugacy class here. So the first step will be to show that the width of X is finite if and only if the abilization of gamma star is trivial. And since gamma is perfect, it will be trivial if and only if it's finite. So I might say some places finite, some places trivial. It's the same thing.
But the right-hand side does not depend on X. So which means that if you would know it for one X, you would know it to any other?
Yes. If I know it for one X.
I mean, you said that X is a fixed conjugacy class, right?
Okay. So okay, I'm cheating a little bit. You are right, Alex. I'm assuming that the conjugacy class generates everything. If it contains some congruous subgroup let's say by the congruous subgroup property, right? And you need to know that the abilization of this congruent subgroup is trivial.
Chen, do you prove now the main conjecture based on Theorem 2, on your Theorem 2?
No, I proved Theorem 2. I proved
Theorem 2. Okay.
Yeah, I proved Theorem 2. So, okay, Alex, I really need not to know just the validation of the full group, but of any congruous subgroup is trivial, of the non-standard model. Yeah, I should have said that I assume that the conjugacy class generates.
I don't understand. So in the proof, you do assume the congruent subgroup property for gamma, or you don't assume it? We are not using it.
Well, formally speaking, you are not assuming it, formally speaking, but you rely on Knesser's proof of the congruent subgroup property.
Well, that's okay. But what I don't understand, so let me still ask my question more. Assume you know it for some specific elements, we satisfy that it's conjugacy class, blah, 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 blah. Then you know it for all like that? That's what you are saying?
No. What I'm saying is, sorry, that's not what I'm saying. What I'm saying that if you know it to some congruous subgroup, the diagonalization of the ultra power of this congruous subgroup is trivial, then you know it for every conjugacy class such that the group which is with such that the group generated by it contains this congruent subgroup. This is what I'm saying. Okay, Alex?
But okay, so now assume you know that the conjugacy class is of finite width for one element whose group, the normal subgroup generated by it, contain this specific congruent subgroup. Then you know that's if and only. So you know that the congruent subgroup ultra product made abelian is finite, and therefore you know it for every element. I don't know. I'm just kind of.
I see what. No, I understand what. So wait a second. What I want to, I understand what confusion in what I wrote.
Even
yes. So but I expect. So okay. So what happens is so the direction that you are asking about. You see, I know that this group is perfect. So if you know that even one conjugacy class as a non-central conjugacy class as a finite width, then you can get these elements by as a product of finitely many commutators, right? Mm-hmm. Because it's perfect. And then when you pass to congruent subgroups, they are not exactly perfect, right? Yeah. So yeah. So this is why I forgot to say this assumption just makes life easier. It is not very essential, but it makes life easier that your element, that the conjugacy class generates the full group. Okay. So the second step is to show that the abilization of gamma start is trivial if and only if a certain central topological extension of the congruence completion of GQ star has a continuous splitting. So if you heard Alex's previous talk, you know that there is a formulation of the congruence subgroup property using central extension. And so step B says to you that you also have a formulation of the question whether or not the abilization of gamma star is trivial using a central extension. So you get a central extension with certain properties, and the third step is to show that every central extension with this property splits. Okay? So I'm going to go over this part. At some point it will be technical, at some point it will be less technical, but please feel free to stop me. So step A is to show that the width of X is less than infinity if and only if gamma star, the abilization of gamma star is trivial. So I don't want to go over this slide. because it's really a little bit technical, but what I want to say that we use this Knesser argument or some generalization of Knesser argument in two places in this proof, and this is one of them. So what you can do, you can use Knesser work in order to show that if you take a conjugacy class that generates a full group, then after finitely many products of this conjugacy class with itself, you cover the set of all commutators. You get every commutator, and once you know that you get every commutator, now the question becomes, does the commutator word as a finite width? Okay, so the actual details are slightly technical. Let's ignore them. Okay, so now we the question is about the set of commutators. So let U be a non-principal ultrafilter on N, and gamma star will be the ultra power of gamma with respect to U. Do everybody know what is a ultra power, or should I explain it?
Nir said it last time, but maybe you want to say a few words. I think nobody will complain if you...
Okay, so I will give the most straightforward definition because I'm not going to use any deep property of ultra powers. You just take the direct product of gamma countly many times with itself. So the elements are sequences of elements of gamma. And you divide by the subgroup, which contains the sequences such that the set of indexes for which the nth coordinate in the sequence is equal to 1. So for each sequence, you get a set, and an element belongs to your subgroup if the set is an element of the ultrafilter. Okay, so it's easy to see that this is a subgroup, and that this is a normal subgroup, and that you can divide. So by the congruence subgroup property, gamma is perfect. So we do use, so you can avoid it to use the fact that the group is perfect. You can use property T to show that the hybridization is finite. But anyway, in the direction that I'm going to use it, you don't really need to know that it's perfect. It's an if and only if statement. If it's not perfect, then the non-interesting part of the if and only if fails. But so actually the proof gives you a new proof. So if you follow this proof, you get a new proof for the fact that this group is perfect without using property T. Okay. I am saying this that just for people who know the proof of the congruence subgroup property. Usually when in the proof of the congruence subgroup property, people uses property T, but you really don't need to use property T. You don't need to know a priori anything about the hybridization of the group. But for this conversation, let's assume that we know that gamma is perfect. A standard argument implies that the width of the set of commutators is finite if and only if gamma star is perfect. And it's such an easy argument, so I want to say it. So if the width of the commutator set is finite, then there exists C such that every element in the product such that every element is a product of atmospheric commutator. So the same is true for the direct product of gamma countly many times, because you do it in each coordinate separately, but then it's passed to the quotient, which is the ultra power. on the other hand, if for every n there exists Gn such that Gn is not a product of the most n commutator, then if you take the sequence Gn, then it is clear that it is not that it does not belong to the commutator subgroup of the direct product, but it's really easy to see that it's also in the quotient. It does not belong to the commutator subgroup of the ultra power. So this is basically the proof. Okay. So now we pass to step B. Now we know that our goal is to show that the abilization of gamma star is trivial. So the abilization of gamma star is, so what we want to show in step B is that the abilization of gamma star is trivial if and only if a certain central topological extension has a continuous splitting. So what I'm going to do, I know that I didn't talk about 5 first, but I want to talk about 5 and 6 together. I will define 2 topologies on gamma star. The first is the congruence topology. In the standard sense, we have gamma star is just equal to G of O star of our group G over the ultra power of the ring. So we have a congruent subgroups in the standard setting, in the standard meaning, and we have a congruence topology, and it is everything that you think it is. It's not everything that you think it is. It's the quotients are not compact, and this will be a problem for us. But beside this, it's everything you think it is. But we have another topology which replaces the profinite topology. And what is this new topology? You take, so you want to define a base of neighborhoods of the identity. So you take regular congruent subgroup and you intersect them with the commutator subgroup. And this is the new base. So I want to say this is slightly unnatural. There would be a much more natural topology to take a finer topology than this topology. But from set theoretical reasons, we take this topology. I will say later why we take this topology.
How do you know that this is a direct product? The gamma star model, the gamma star C of I is a direct product of the gamma star?
Because in the right quotient, I know that the right side is a perfect subgroup. Exactly because I know that the right side is a perfect subgroup.
Because what?
The right side, you have the abilization times the congruence quotient, and since gamma star is perfect, also this quotient is perfect. So the commutator subgroup project onto.
No, I don't understand. Gamma star, now you assume it is perfect.
Sorry. You are perfectly right. Okay, in gamma you agree, right? If it wasn't gamma star, if it was gamma, it's clear, right? Because it's perfect.
Yeah.
Now, you don't know that gamma star is perfect. This is what we are trying to prove, but you know that this congruence quotient is perfect because in this congruence quotient, not only that it is perfect, but every element is the product of a bounded number of commutators. You have a uniform bound because this in the standard model.
You
right?
mean after? So you mean now you're talking about the left-hand side?
No. I'm talking about the right. I'm sorry, I don't know how. Do you see my cursor? Or no?
See.
I'm talking about the right-hand side. Forget for a moment about the star, okay? Think about gamma.
Yeah.
What I'm claiming is not only that this group is perfect, every element is a product of a bounded number of commutators, because this is just p-adic groups, and in p-adic groups you have dimension, and the number of commutators you need to take is bounded by some function of the dimension.
Yeah, okay.
But this is already a first order statement to say that the congruence quotient, every element is a product of at most 1,000 commutators. This you can say in a first order language. So this passes to the ultra product. So you get also in the congruence quotient of the ultra product is perfect. You don't know the group itself, but the quotient is perfect.
Well, I understand, but why you can split off the abelian part of it, the abelian quotient as a direct product? If you have,
I do not understand. The gamma star C is defined the way that we.
I see. So this is just because both are quotients. You have an abelian and a perfect, yeah. And then it must be the. I see. It's kind of elementary group theory.
Yeah. Once you know that the right hand side is perfect. Once, yes.
Mm-hmm, mm-hmm.
And everything is natural, so everything is commute. So this diagram commutes. If you have an ideal which is contained in another ideal, then everything behaves nicely in these topologies. In these two topologies. So what you get, and you can take completion with respect to these two topologies, but now we understand what is the congruence completion. Because of the splitting, this is just, if you look at it, this is just the abelization times the congruence topology. And this is very important to us, to be able to compute the congruence topology directly, because this is the reason that we take such a strange topology, not a more natural one, is because if you have inverse limits of compact sets, they are always non-empty. But our quotients are no longer compact, they are discrete infinite groups. So we do not know, so we know that the inverse limit is not empty simply because the groups sit inside it. But for example, a priori, there is no reason to expect that the map from the congruence topology to the congruence topology will be on 2. There is no reason to expect that it will be surjective. It is surjective because we can actually say exactly what is the congruence completion is. So now the problem becomes, you have the map, the natural map from the congruence topology to the congruence topology. It is surjective, so you get, and it is clear that the kernel is the abelization of gamma star, and that this kernel is central. So you have a central extension, a central extension. But at this point, it gives you nothing, right? You have a central extension, so you formulated the question in a slightly different way, but you still need to prove that the abelization of the abelization of the gamma star is trivial. You didn't gain anything at this point. You just gave a new formulation of the problem. But now we do what we do in the congruent subgroup problem. We want to extend the topologies to topologies over GQ star, over the non-standard rationals. And in the congruent topology, this is easy. This is work from the same reason. There's nothing deep about it. But because we chose such a natural topology for the congruence topology, this is completely not clear that it can be extended to GQ star. And again, we use Knesser's proof of the congruous subgroup property of the centrality of the congruous kernel in order to show that you can extend it to GQ star. Heuristically, what you want to do is to take a finer topology than the congruence topology, in which it is clear that it extends to Q star, but it is not clear that the kernel is central, to use the same argument as in the standard congruous subgroup property to prove that it is central, and then to take a quotient of this completion to get what we call the congruence topology. But you can't do it this way because of set theoretical issues. So you have to work a little bit differently, but the bottom line is that you can extend it to the non-standard rational points. So what you get is you get a new central extension of the congruence completion of the rational point, but it has the same kernel as the original central extension, and this is the important part. So you want to prove now that the kernel of this extension is trivial. And this extension has several properties that we are going to use. First, this is just the abelianization of gamma star, so this is a discrete group. You have a continuous section psi1 over the congruence completion of geo star simply because, sorry, wrong direction, because of this, because we can compute the congruence completion. And C, because these are completion, we have a section psi2 over GQ star, which is dense in the image of the congruence completion. So avoid the last sentence. I will get back to it in a minute. So what is the advantage to work with rational elements and with non-standard rational elements and not a non-standard integer element, is that we can show that every element, this is again basically due to Knesser, that every element of GQ is a product of a bounded number of commutator. So this also true in the non-standard model. So you get the GQ star is perfect. And once you get the GQ star is perfect, it is an easy exercise in topological extension to show that this is trivial if and only if the topological extension, this topological extension has a continuous splitting. This is just an exercise about extensions of topological groups. So call it. So we are not going to work with this specific extension. We are going to prove something more general, which is in some sense equivalent to the fact that the metaplectic kernel is trivial. So we are going to call it topological central extension a discrete GQ star metaplectic extension if it satisfies the following properties: this discrete, eta as a continuous section psi1 over an open subgroup of the congruence completion of GQ star. And in this talk, I will always assume that it has a continuous section over G of star because it's just simpler to assume this. And we have another section which we don't know that it's continuous or anything over GQ star, the discrete group, which has a dense image in E. So under this assumption, we will show the such a topological extension must split. Okay. So the third step is to show that every discrete GQ star metaplectic extension has a continuous splitting. So you have such extension, and as I said, we assume that it has a continuous splitting over the congruence completion of Geo star for simplicity. And there is something beautiful, right? All our problems come from the fact that our group is anisotropic. If it was isotropic, everything becomes simpler. We have unipotent elements, you have much more machinery in end. But the congruence completion do not know if the group is anisotropic or not. This is something that depends on the real places. The congruence completion does not see it. So in this specific case, it's even simpler. You actually have an isotropic group, not just an isotropic group, a standard Chevalier group, such that its congruence completion is exactly as the congruence completion of your group. So we take F prime to be the sum of n hyperbolic plane, and H is spin of F prime. So this is a standard Chevalier group. And there is a topological isomorphism rho from the congruence completion of GQ star to the congruence completion of GQ star. Just take the isomorphism without the star, and it induces an isomorphism with stars. It's simple. And not only you have this isomorphism, this isomorphism is nice with respect to the structure of orphan subgroups. It sends the integral point to integral points.
I don't understand the trick here. So you change the form of the group by taking a different quadratic form?
Yes, but now it's isotropic.
Yeah.
So I have an isomorphism between the profinite completions.
I see. The single prime completion, I see. Without, wow, I see. Oh, very trick.
So now you get an extension of a Chevalier group. And you know that you still have a continuous section psi1 prime over the open subgroup, which is the closure of the integral point of H. What you don't have a section over HQ star. This you lose. You lose this effect. You have a section over the closure of HO star, even a continuous section. You have a section over a row of GQ star, but you don't have a section over, you don't know that you have a section over G of Q star. And as we shall see in the next slide, this is the point. This is what we really have to prove. So now you don't have to use it, but it makes life simpler to use the fact that HO is boundedly generated. So the fact that it's boundedly generated is pretty much equivalent to the fact that commutators in HO, the set of commutators has a finite width. So this path to the ultra power, so you get that H of O star, which is in the intersection of AQ star with the closure of H O star, is perfect. You get that this intersection is perfect. And you didn't know, and you recall we didn't know, this is the whole point of this whole proof, is to solve that G of O star is perfect, but the fact that it's H of O star is perfect, we already know. So now come the points. You have that, you know that you have a continuous section over the congruence completion of H of star. Assume for a moment that you knew that you have a congruence completion over HQ star. For some reason, somebody tells you you have a section, sorry, you have a section, not necessarily continuous, not necessarily anything, over HQ star. So there is a priori, there is no reason to expect that if you take these two sections and you look on them and the intersection of the domain, that they will agree. There are two arbitrary sections. However, if you have a central extension and of a perfect group, you only have one possible splitting. You cannot have two splitting if the group is perfect. Since this intersection is perfect, if you know that edge Q star has a splitting, then these two sections will agree on their intersection, and then you can glue these two sections together to get a section of the congruous completion of HQ star, and then you get the sequence, the central extension split, which is exactly what we want to prove. Okay, so now the question becomes to show that you have a section over edge of Q of star. So what is the advantage in this question is that you have a well-developed theory of central extension of edge over field, of Chevalier groups over field, of central extension of Chevalier groups over field. And I don't want to go into the details because I have just 5 minutes and I want to leave time to details. But you have a theorem of Metastoma that tells you exactly when such extensions split, and it's related to commutators of certain lifts of elements. You need that this commutator will be trivial. And then what you do in order to show that they trivial, you approximate these commutators by commutators of the splitting of G of Q star. You know you have a splitting of rho of G of Q star. So if you take two commuting elements in rho of G of Q star and you lift them with the splitting, they still commute. And it turns out that you can approximate the elements that you need to show that the commutator is trivial in order to apply Metastoma theorem. You can approximate this element by commutators that you know that they are trivial because they come for commuting pairs in GQ star. Okay, so I didn't explain the last step, the details of the last step, but I think that it will be too much to do it right now.
No, but maybe you can still say a little bit why the generalized Riemann hypothesis is relevant.
Yes, it's because of the approximation. So in the what you actually prove in the standard congruent subgroup property in the anisotropic cases is not that the group is trivial, but that the kernel is divisible. And if it is divisible and profinite, it is trivial. So in the standard congruent subgroup theorem, this is profinite, so it is enough to prove that it is divisible. So if you use similar arguments to the standard argument, you can show that this is divisible without assuming anything, and this would give you that the set of power of finite widths. But if you want to work with the set of commutators, a priori this D could be a vector space over Q, the line abelian group of a vector space over Q. It's possible, and then the approximation that you need to do, in the last step, you need to do a much better approximation than you do in the standard congruent subgroup. In the standard congruent subgroup problem, and for this you need the general Riemann hypothesis. Again, it might be able to avoid it your base ring has enough units, but this is a totally number theoretic question about a certain version of Artin primitive root conjecture.
Very nice. I like very much this this trick, which I didn't know before, that you are passing from the isotropic group to from the anisotropic group to an isotropic group with the same finite completion. You know, you kind of after localization, but now you have used before several spatial properties of the orthogonal group. Is there a chance that you can overcome them in order to prove even a single new case of the congruence property? I allow you to, you know, to kill all the periodic, namely take localization in all the problematic primes, etc., so that you will get something like isotropic.
Okay.
Because, in fact, the last step would work.
Okay, so everything works. The only thing the only thing that doesn't work is step 9, which is similar to the fact to prove. So step 9 is the problem, but I'm sure that if you our method to prove step 9 is using the machinery of the congruent subgroup property, that you can extend the congruence topology to GQ star. I do not
really, I mean, because this looks like something which is, if you would not say that this is a problem, I would buy it without
right.
Even. So you said that this is such a crucial issue to extend.
This is a very crucial issue. Again, you can define a finite topology for which it's clear that it's extend, but then you have two problems. The first is set theoretical problems. Let's forget about it. But the second problem is you again return to the situation that you don't know that the kernel is central, and then which is what you don't know in the congruence subgroup problem. Yes, this step relies on Knesser deeply. Once you know Knesser, it's in some sense a computation, basically computation at least, but it's not trivial. At least I don't know how to show that it's trivial. This is the point.
No.
Sorry, Alex, for showing that commutators have finite widths. Not, this will deal with this will show to you that in Rapid-Chook lemma you don't get a billion groups. It won't solve the full congruence subgroup problem. As I said, we use Knesser in two ways. First, to reduce the question to commutators, and then for step 9. If somehow by some argument you can prove step 9, it will only give you that commutators have finite widths. Instead of and that in Rapid-Chook lemma you don't get.
Someone understands. So you mean it in the Rapid-Chook lemma? I apologize for the people who are not really familiar, maybe with all this delicate point. By the way, Rapid-Chook will talk next week in the seminar, and it's maybe my fault because this talk is very general and it probably should come earlier, but somehow I didn't think about it, and then I heard him giving a talk in some Zoom conference, and I like it so much. I asked him to talk here to give exactly the same talk. Anyway, but let's go back to the Rapid-Chook lemma. So, are you saying in the Rapid-Chook lemma there are two kind of parts? I think maybe describe a little bit of this. The nanobillion, the simple group, nanobillion simple group, and a billion. Are you saying that the nanobillion can be resolved? Can you?
No, I'm not saying that. No, I'm not saying. I'm saying that the nanobillion equivalent to the fact that I'm not saying anything smart, Alex. I'm saying that finite commutator width implies the fact that it
implies what?
We'll show to you that in the aperture lemma you don't get abelian groups, but this is not surprising. Like if I would say to you that, roughly speaking, this okay. So I'm not saying anything. Okay, yeah. Yes, it will tell you something, but if you can, I'm not saying something smart. I'm saying right what we do here. We prove that the abelization of gamma star of, or if you want a general thing, the abelization of every congruent subgroup is trivial. But if it's true in gamma star, it's true in gamma. And if you know that the abelization of congruent subgroups in gamma are trivial, you know that in the Rapinchuk lemma you don't get abelian groups. So the way that I want to so I think that the point of this work is not that I don't think that the proof itself gives you anything new that you didn't know before, but I think that the formulation of the conjecture is the right formulation, and the goal was to show that this conjecture can hold in also for anisotropic groups, that, you know, because otherwise what's the point? And the hope is that now that you have this conjecture, you can use new methods, for example, from number theory, to solve the conjecture, because this conjecture is some type of wearing type problems, right? It's possible that somehow it will be easier to approach the conjecture than the congruent subgroup property, or the but this is not something that we did. The proof that we gave is, if you can do a proof along the guideline that we did, you probably can prove the congruence subgroup property directly.
Okay, very nice, very interesting, all these connections. Are there other questions? If people in the Zoom wants to speak out, because I cannot see you. If not, so let me thank Chen once again. Thank you very much, and see you all next week when Rapinchuk